So our first speaker of today is Michael Coons from Bielefeld, and he's going to speak about spectral theories of regular sequences.
So thank you, Nico. I should say thank you, Bob, for having a conference in Toronto. It's kind of nice to be back here. I was a postdoc here more than 10 years ago. I thought it was less, but time kind of catches up with us all, doesn't it? So what I want to talk to you about is essentially some connections between number theory and aperiodic order. And there's some connections that are there that I kind of show, and there's other ones that I really hope are there really, really badly. And that's kind of in work to come. Yeah? And the objects I'm going to look at are generalizations of substitution systems. So I think substitution system is something at least the aperiodic order crowd really has a handle on, understands well. For me, when I think of substitution systems, these are always finite. Yeah, over finite alphabets, they go to finite words. Some interesting things happen. They've been studied sort of number theoretically, going back to long time ago when, if you look in this old book of Whittaker and Watson, right? This is this one where Whittaker should be second, but he's first. Yeah. In 1902, he looks at the sequence, or the series, I should say, the sum of z 2 to the n, right? And I guess n bigger than 0 here. Yeah. And so this is, it's just the coefficients of this power series are 0 if it's not a power of 2 and 1 if it is a power of 2, right? You can write down a finite automaton, deterministic one that kind of gives you this sequence, that recognizes this sequence. So there's a nice substitution system with constant length that gives you this sequence. And for him, what was interesting about the sequence in this analysis book is it's actually a really easy function that has the unit circle as a natural boundary. Yeah. And so what happens, I guess, if I call this, let's call this A for lack of a better word here. So what you get something like A of Z is, what is it? Z plus A of Z squared, I think. Yeah, and so certainly 1 is a singularity on this, right? So 1 is a singularity here. So that means any square root of 1 is a singularity, and you kind of play this game going back and forth, and you get that any root of unity of order power of 2, yeah, is a singularity for this, right? So you can't escape the unit circle. And it's kind of a slick example. So that's going back to 1902, which sort of, one would say kind of predates the modern theory of substitution systems. And also predates the modern theory of Mahler functions, because Mahler wasn't, gosh, it might have been the year Mahler was born, but I've made that mistake already once this week. So, so this is sort of the number theoretic side. And when you have this, what you get is that this function, because it has the unit circle as a natural boundary, you get that A of Z here, so I'll just write A of Z, is transcendental as a function. Yeah, transcendental. And I guess I mean over the field of rational functions of with complex coefficients. Okay. Of course, showing a function is transcendental is often much easier than showing its special values are transcendental. But we'll get to that a little later. Okay. So this thing, though, this comes from a substitution system with finite things, right? So I want to extend that and look at sequences that have infinite values. Okay, and here's how one does this. Here's how I do this, I should say. Okay. So Aleutian Shallot in the 90s, in generalizing automatic sequences, which was sort of their forte, yeah, defined what was called a K-regular sequence. Okay. So a K-regular sequence is a special, oh, this is the one I want. Yeah. So what you do is you define this K-kernel. Here's the sort of the combinatorial way and the way probably substitution people like it. And the K-kernel of a function f, yeah, is you look at all of the special subsequences of f, where you're sort of looking at a common difference of some power of k. This k just chosen, yeah. And you look at this, what on the division algorithm you would write, you'd split everything up into arithmetic progressions, and you say, okay, what about this set? Yeah. It turns out if this set is finite, then you're automatic, which means you have a constant length substitution system. Okay. Well, it might not be finite. And so the kind of the next best thing is say this thing is, if I generate a vector space with this, it's finitely generated. Yeah, and I'll give an example on the next slide. Okay. This is equivalent to actually having, say, a finite set of matrices. Can I just point? I think people can read as I go. This is my favorite pointer, right? it's equivalent to have a finite set of matrices. And what you do is you sort of mimic what a linear recurrence does. Now, if you remember, a function's linear recurrent if you have one matrix, square, right? A couple of vectors. And to get the nth value of the linear recurrence, you take powers, the nth power of this matrix, and then multiply your vectors on the side. Yeah. So what this is doing is say, well, let's take away this sort of power version. And what I'll do is I'll write n in the base that I care about. That's this k that's connected to the k kernel, one that's finitely generated. Yeah. And then what I do is I have a matrix for each k-ary digit. And I just multiply them in a way that you choose, kind of forwards or backwards. Just once you choose it, you stay that way. Okay. So you can see lots of things sort of right away. And so this is a regular sequence, forms a regular sequence. And you can see, well, they can't grow too fast, right? For example, a regular sequence can't grow exponentially because if you look at the norms, I have at most sort of log n matrices. Each matrix has a finite norm. So this thing kind of grows like, at most like a power of n. Yeah. So some constant to the, or log n to some constant. Yeah, or constant times log n, I guess, to the log n. Okay, so these are the objects I'm sort of interested in. Here's an example. This is, I think, my favorite example. So this is called the Stern sequence. It's given, if you like, by, now that it's up higher, I'll try this. Oh, again. It's given by a couple of recurrences. So if I'm thinking this thing turns out to be 2 regular, yeah? And so when I multiply by 2 inside, I get the same sequence back. So S of 2n is S of n. And here, what I do is kind of split over the sum. So S of 2n plus 1 is S of n plus S of n plus 1. And I start off, initialize with the values 0 and 1. I can just define my sequence that way. And I get some sequence. It turns out the sequence is regular. And that's given just because of those 2 recurrences. Yeah. And I have what I would call the linear representation. So on the page before, it turns out my matrices are sort of this is this Fibonacci matrix, I guess, and it's transpose. Yeah. And what we do is we essentially form all words of a certain length corresponding to base expansions and see what happens. And so here's how the sequence starts. I've drawn this kind of in a funny combinatorial way. So it's usually called is Pascal's triangle with remainder, or with memory, sorry. Yeah. So, you know, in Pascal's triangle, usually you sum 2 things and you forget the things above it. But here we keep them. Okay. So I'll start off with sort of a 0, 1, 1 triangle. Yeah. And then 1 and 1 is 2. I keep the 1s, which you do in Pascal's triangle too, right? It's kind of funny. And then I have a 2 though. So now what I do is I keep the 2. You see, as I go along, I keep the 2. And now 1 and 2 is 3. Okay, on either side, I keep the 3. And so on and so forth. And to make the sequence, I just erase that right side of 1s and just read this as you go, like you'd read a book. And that's the sequence. So you can see it's sort of palindromic between powers of 2. Yeah. And these things kind of correspond to if I had a substitution, I keep applying it, and that the word that I apply it to grows, right? So this is kind of the, say, the analogous way of writing down larger and larger words of, say, a 2 or more sequence or something. Okay. All right. Why this sequence? Well, yeah.
I'm sorry.
Sure. If you like, just imagine, get rid of the sequence if you like, okay, up there, and erase all this. Just start with 0, 1, and 1. Now I do the same thing as in Pascal's triangle, right? So I keep writing 1s, and I have the sum of these 2 is 2, right? Now what I do is I keep this pattern, okay? And I always keep 1, 2, 1, okay? I keep a 2 once I have a 2. It means I don't erase it.
No, but I mean, like, it's a moving target. That's the part I'm having trouble with.
Maybe I'll write it down really quickly over here. Maybe it's better if I just form it, right? So I go like this, 0, 1, 1. Now, here's Pascal's triangle. Now I'm going to mess this up, right? Maybe, do I start with 1 and 1? I don't know. Yeah, so it's a little different. You'll have to help me on this one because I'm used to this one now. So, but now I go 1, 2, 1, right? Okay, so now I'm kind of doing the same. So far, I've kept everything I ever always have, right? But then I go 1, 3, 3, 1, right? Because I add. But somehow I've lost this 2. The 2 is now gone. I'm keeping the 2. So in over here, what I do is this.
Why are the 3s going straight down?
Well, because I wasn't very good at drawing my picture. I could have squished it, right? I mean, they are kind of going straight down, but they get more in the middle, right? Because eventually what happens, so the 3, I mean, I have to put 5 between those, right? And I have to put 4 between those. So if I want to keep the things that are straight, then my picture gets really small and my font can get small. But you could do it that way. Yeah, is that okay? Cool. Okay. So why is this sequence interesting? Well, the first and foremost, if you're a combinatorist, it turns out it's Herb Wolff's favorite sequence, I guess, or was, I should say, Herb Wolff's favorite sequence. And I guess if you're a combinatorist, that's enough to make things really interesting. Yeah. For me, the nice part is it actually has enough structure, or enough complication, one should say, to where if you look at the ratios, S of n over S of n plus 1, you get all the non-negative rationals. You get them already reduced and without repeats. It's more or less this sort of fairy fraction type organization. Yeah. So these are kind of related to the Sturm-Brokat polynomials, or Sturm-Brokat sequence as well, Brocault, I should say. And you can kind of see, if you guess, if you want to think about the maximum values, you see this sort of Fibonacci sequence thing popping up. The maximum values between powers of 2 are the Fibonacci sequence. So as I went over here, like you see kind of what, 1, 2, 3, 5. And it's because of this additive structure, essentially, that you get that. Okay. So here's what it looks like between a couple of big powers of 2. I think of this as like the cathedral picture, right? Because if you blur your eyes, right, it looks like kind of a big Gaudi's cathedral or something, right? And you can really see this sort of palindromic picture happening, right? And these are your Fibonacci values way up high. And if you look at these Fibonacci values, what's interesting is you see that's like about 1/3 the way through you've got one, and about 2/3 the way through you've got another one, because of the, yeah. And 1/3 is kind of a nice number, right? It's a nice rational number. So the maximal value kind of happens at a rational sort of distance. Okay. Now think of, here's a picture of the mean value of the sequence. Now I can't say mean value because it's not finite value, right? When you have a finite set of values, you always compare it with 1 over n, yeah? But the sum of this thing is a little bit different. So the right thing to compare it with is actually n to the log base 2 of 3. And why that's true is because between powers of 2, the sum of this is 3 to the n. Okay. And so this is in the log scale. So every one of these things that looks like a period is actually double the length, right? So these are kind of between powers of 2. So if let's see, is this going to work for me? So this one on the end here, where I've got kind of 11 and then 12, this is sort of between 2 to the 11 and 2 to the 12. Okay. And there's this naturally sort of doubling structure, like the words in a substitution system, right? And I want to compress that so I can see patterns. Okay. So this one's kind of nice. It looks a little bit foresty, nice hills, looks kind of smooth, right? Yeah. Another kind of famous example of a regular sequence, and maybe simpler than Stern sequence, is the sum of the bits of a number. So I write my number in binary and I sum the digits. Yeah, so the number of 1 space 2. It's also a regular sequence. And that one turns out to be very smooth. If I look at sort of the mean value, there's this old theorem of Dilation that's very smooth. It's something like, was it 1/2 n squared log n or something, yeah? And so you don't get this repetitive sort of part at the front, but you do if you look at the error term. So this is the sum of the binary digits. I'm summing off to n, and I'm taking off the smooth part, okay? The n just is because it's n squared, I wanted it to look like a mean value and get my terms right, yeah? And this is sort of what you get as that periodic piece. So now it's looking a lot different, yeah? At least I think of this as a lot different. Someone suggested a few weeks ago when I showed this picture that this is less like a nice smooth hill and more like the Dolomites. Yeah. And if you want to do sort of calculus and things, you'd hate to look at this picture, but maybe you'd like to look at that picture. Yeah. Maybe. All right, so how does one think of regular or of sequences in general? So as a number theorist, in the past, I've taken sort of the enumerative combinatorics point of view. Yeah. So you have a sequence. You want to do something with sequence. What you do is you attach an analytic object. Quite often, for me, this object was a power series, the generating power series. Yeah? And then you can ask kind of all of the usual questions, sort of going back to sort of Fatou's results on transcendence and things like that in the very early part of the, in fact, about really close to 1902 when this example was used. Yeah, and you can ask, okay, what kind of function is it? Is it a rational function? Well, that would be nice. Yeah, then you have a lot of structure and you can talk about the coefficients, and the coefficients are a linear recurrent sequence. Yeah, you could have an irrational algebraic function. That's a bit weirder. Yeah, so you could have a d-finite function. These things come up. So a d-finite function means that it's the solution of a linear homogeneous differential equation. Yeah, something like the exponential function is a differentiably finite function. Those things are also, when you're on the sequence level, these are often called polynomially recursive. So sort of like these a-pair sequences that have to do with the rationality of zeta 3 or fall into this category. And then you have these what I call these last two buckets, I think of them. You have transcendental functions. Actually, I said differential algebraic. Let's not worry about that. Then you have this big thing called transcendental functions. So transcendental functions are actually quite different from all of these things. Every one of these other bins, rational, irrational algebraic, differentially finite, even differentially algebraic functions, those tell you about the structure of something. Yeah, it actually gives you information that you then might be able to go use. When you prove a function is transcendental, well, as a number theorist, you prove a number or a function is transcendental, you're really happy for some reason. That now I get a little bit more lost. I don't know why I'm so happy. Because what it means is you don't really know anything about the structure, except you know it's complicated enough to not fit in all the bins that you thought would be there. Yeah, so it's a non-result. It says something's not algebraic. And you go, all right. If you get lucky, you get some approximation properties, which tell you something, but in general, you're just kind of, I'm in Canada, you're kind of boned, right? Like it's, yeah. Okay. And what kind of questions do I want to answer about these things? Why am I unhappy with transcendence, right? So there's sort of three questions that pop out to me when I think of regular sequences. Okay? And this is something that might be a little bit different than substitution systems and some related. So the first one is about maximal values. Yeah. So I have now a regular sequence that if it has an infinite number of values, well, what are the big ones, right? And where do they occur? It's not really a question you can say ask for substitution sequences, or maybe it's a less interesting one, right? Because you have a finite alphabet. I mean,
quick question. Is that for the slide 4, do you know that your algorithm for generating functions actually?
yeah, so in fact, because of the growth condition, it doesn't grow algebraically, it grows almost like a polynomial. So in fact, that means that if you have a regular sequence, this thing has the unit circle, at least as it converges in the unit circle. Yeah. What's also interesting, and it's nice to go back and not go back myself. It turns out if you have a regular sequence, it's either rational or it doesn't fit essentially in any of these other ones except transcendental. It's not necessarily easy to see, actually. It's sort of easy to see if you imagine they all kind of look like this, right? Because these all have the unit circle as a natural boundary. Well, if you have a differentially finite function, this thing can have at most a finite number of poles. These are meromorphic functions. Yeah, and so you play this game. This one down here, the differentially algebraic one, that's highly non-trivial and not easy to see. And this is the work of sort of Boris Hedrachevsky has pushed. It's quite interesting, right? But quite deep. Yeah, much deeper than I would say these other ones. Yeah, at the function level especially. Yeah. So you have this sort of rational or transcendental, and that's the point is I know these things are not rational, they're transcendental, I have no information. Yeah, and so, yeah, so at maximal values, what are they? Where do they occur? Yeah, the spectrum of values. So the Stern sequence was cool because it took every single value. Yeah, now not all regular sequences take every single value. Certainly ones that are connected to substitution systems don't. Yeah, but is there a way to figure out what they are? And is that an interesting question, right? And then you can talk about maybe the distribution of values. Yeah, so for example, if you have a what I would call an automatic sequence. So it's the fixed point of a constant like substitution. Yeah. The distribution of values is quite interesting. It's usually Cobham's theorem, right? If a value occurs and it has a density, then it's rational. Yeah. So that's pretty cool. Some similar things are known for regular sequences and maybe make that a more vague or more interesting question. Okay, so maximal values. What's interesting about maximal values? Well, maximal values are connected to the so-called finiteness conjecture or the finiteness property. Yeah. So remember, I have an underlying finite set of matrices. Yeah. And so if you imagine standard rho here is going to be the spectral radius of a matrix. Yeah, so that's the absolute value of its largest eigenvalue, right? Okay, and so what we do is we're going to extend that to finite sets of matrices. Yeah, so if I have a finite set of matrices, sort of the natural thing to look at would be, well, I take, say, products of all words of length n for any n. Yeah, but what I do now is I look at the maximal norm of those products, and then I sort of normalize by the length of the word. That's this one on n. Yeah, I take the maximum value and I look at the limit. And I call this the joint spectral radius of the set of matrices. Okay. It turns out that this thing exists, which I think is kind of cool. This goes back to Jean-Carl Rode and Gilbert Strang, I think in the 1960s. It's a kind of short paper showing this exists and some cool properties about it. Yeah. And so a set of matrices is said to have the finiteness property. Yeah, now I'll just point. If there's some finite product, sorry, let me get that out of the way. Okay, some finite product in the semigroup that is generated by your finite set, so that the normalized spectral radius, so if I have a word of length m, I still want to kind of normalize by the length, yeah? The normalized spectral radius is the joint spectral radius. So in other words, you're looking at this limit on top, and you're going, does it actually reach the limit at some point? Yeah, is there a finite step, so finiteness property, where I actually get to be the limit? Yeah? And so I get Jeff, I don't think I've ever said this with Jeff Ligarius to the audience, right? So Jeff Ligarius and what was the Wang's first name again? Yang Wang. I don't know how I forget that, right? Conjectured that this finiteness property holds, and I believe they conjectured it holds for all real sets of matrices, but then there were some counterexamples found for the real case. And so I've modified their conjecture to say the finiteness property holds for all finite sets of integer matrices. Okay? So integer matrices are a little different, right? We suppose some sort of gap results maybe hold Diophantine things. Maybe it still holds for this. Everyone I know kind of believes that this probably holds for integer matrices, but a counterexample would be cool too. I don't have a lot invested in this. I just want to know. Okay. Yeah.
In the definition of for star, you know, you assume that I2 is bigger or equal than I1 or not?
No. So this thing right here. Yeah. No, take all patterns.
Okay,
all patterns. Yeah. So you have k to the n words that you're looking at. Yeah. Everything. Yep. Yeah. Order doesn't matter, because it essentially this is sort of like looking at different values of your regular sequence, right? And you want sort of all base expansions that you're looking at. So this kind of corresponds to all words. Yeah. Okay, so there's one of these questions. How about spectrum of values? Why would you want to know that? So other than the Stern example, here's a question where you might want to know that a regular sequence takes every value. So Zaremba's conjecture is somewhat famous in number theory, and it's somewhat unknown probably to people outside of number theory because it's a little technical. So you take your, say, ordinary continued fraction expansion, and what we do is we say, well, if I take these partial quotients and say they're only from a finite set, and let's choose, say, 1, 2, 3, 4 out to some bound, right? Say k, for instance. Yeah. And I look at the finite cutoffs of all the possible continued fractions I can get. So these these convergents, and I look at the denominators of those. The question is there a k? So when I look at all the continued fractions, right, with 1 up to k as partial quotients, and I look at all the denominators of all the convergents of those, do I get the set of natural numbers? Or do I get a set of density 1 even? Yeah. And so this is exactly Zaremba's conjecture. He said there is a positive k such that in fact, all the denominators equal the natural numbers. But you can say that that's, say, just density 1 is quite good. It happens to be known now. I think you get density 1 for, gosh, I don't know what k is. Maybe it's down to 5, something like that. Yeah. But what's nice is you can encode the denominators in a regular sequence because you have this sort of nice way, these nice recursions that the numerators and denominators of the partial quotient satisfy. So if I want to look at, say, just things that have partial quotients 1 to k, I look at all products where these partial quotients now, these special matrices, I have k of them. Yeah. So it's kind of nice to put this into a k regular sequence and just see what happens. Yeah. The case I'm actually really interested in is what if I take just A1 to be 1 and A2 to be 2? Okay. So very little is known about this, and it's wondered if you look at sort of the partial quotients, the denominators from partial quotients just from continued fractions with 1 and 2 as their partial quotients, do you get even a positive density of denominators? Yeah, I don't know. But let's build a sequence out of that. So here's the regular sequence. I call it the Zaremba sequence now, where what I've done is I've chosen these special matrices as my matrices for my regular sequence. And what I want to do is I want that denominator, so I want to lop off the top left-hand corner of any product I get. And that's why I'm using these vectors 1, 0, sort of on both sides, because that takes off that upper left-hand corner. And this is the resulting sequence in the same patch as I showed you the Stern sequence before. So between some of these powers of 2. I've lost the churches, right? Or the mountains. It somehow is, you definitely see there's some sort of self-similar structure going on, right? But it is what it is, right? Now, if you look at the mean value of this, you get a picture a lot like the remainder term from the binary digits one. So I've just printed the 1. I didn't do all of them, right? I've given you just the period part, yeah? And it turns out the right thing to do is now look at the sort of this mean where you look at compared to x squared. Okay. Maybe more interesting for me, right? So I looked at this and I said, oh, it looks kind of like a thing I've seen before, right? And so this is the Takagi function on the right, or the Blanc-Manche curve, or it's got a few different names, fractal geometry. And I thought, boy, it looks kind of similar I should have turned it around and squished it a little, right? But this sort of doubling or halving, or there's something geometric. And so we looked at this picture, and this must have been 2017 or something when I first produced this picture. And I thought, gosh, something geometric must be happening, yeah? And this is not kind of sort of something you can pick out by looking at the power series. Yeah, I want to understand these things. Okay, so this essentially led to a geometric approach to these things. And so I should say via measures. So this is where it sort of connects to this, one should say the zeitgeist of aperiodic order maybe, right? This connection to measures, yeah. And so something that we realized, and this, I gave a talk in Sydney, I think, and Michael Bach was in the audience. And I talked about probably some transcendence results. I can't really remember what I was talking about. And he said, oh, this is cool. So he realized that I'd written on the board that if you look at the Stern sequence, this is this S again, that when you sum the sequence between powers of 2, you get a power of 3. And he said, oh, that should allow one to sort of normalize. This is sort of a volume you can average by and maybe produce a measure, right? And so what we did is we produced these pure point measures. So you take the Stern sequence between towers of 2, right? And let's squish it to the interval, right? So we're kind of in this measure world, yeah? And at the evenly distributed, say, dyadic rationals of a given height, yeah, we just plop a mass on them that is the Stern sequence. So we weight it by the Stern sequence. Now, of course, these things grow really high, but this is why we average by the full volume, which is this 3 to the n, right? So each one of these mu n's is now say a pure point probability measure on the interval. Yeah, that's kind of cool. And you go, well, what happens if I look at the limit? Does it exist? What is it? What's it look like? Can it help you in any way, right? But it's sort of immediate that one should do it. And as an alternative now to this, rational, transcendental, d-finite or whatever, we have Lebesgue decomposition. And it's something I think people in the number theory community haven't really looked at that much, is to say, well, you give me some sort of nice function, which has a beautiful structure, and I would say finitely generated K-kernel. This regular sequences have, I will call it at least, beautiful structure. And can I place them in here? What is the mix, right? I produce this measure, suppose it exists. I now have Lebesgue decomposition. What does it look like? Let's see, right? And so we did this with Stern sequence, and this is the theorem that Michael and I produced. It says, in fact, you can take the limit, and the limit turns out to be an infinite convolution of these delta functions. Okay, just kind of a nice one. And the Fourier transform is a Riesz product. This is where my language is bad. This one's the Riesz product, but not the convolution one, right? It should be, and we just use it all. But so you have a nice Riesz product, and it kind of looks like the one for 2A Morse, right? I mean, it's got a trig function in there, except you've got this 1/3 sort of burying you, right? But that's because the these things grow, right? You need to normalize as you go, right? So this 1/3 is kind of keeping you honest, let's say, if you're a Fourier transform. Okay? And it turns out, in fact, that this is a purely singular continuous measure. Okay? So this pattern that I was looking at for the Stern sequence, it looks smooth, but it's not really. That's more or less what that's telling me. Yeah. Okay. Now, I had this nice functional equation for this A series here. I guess one would call this the Kempner series, maybe. If I was doing number theory for the Stern sequence, which I did for a long time, and I produced just the standard generating function, yeah, I always shift it by 1 because I don't like to start my generating functions with a 0 term, right? An S of 0 is 0. So let's start it that way. Turns out you have a nice product formula. Yeah. And what I've done is instead of just doing this to convince myself, what I've made is this, what do you say, more reflective or something, right? I pulled out the central term, let's say, and now I have sort of a z to the minus 2 to the j, a 0 and a 2 to the j. And then you look up here and you go, can I do this? Well, look, there's a 0 and a 2 to the minus m and a minus 2 to the minus m. It's looking pretty similar, right? So the idea is now, well, maybe one can take all this number theory stuff you know and actually translated it into understanding these measures. Yeah, what's cool is it turns out this is kind of the case, right? All right, so this is the, when I produce the distribution function of the Stern measure, you get this picture, okay? I should say Uwe Grimm actually did this picture for us. He was quite good at these things, yeah. And it looks really smooth, yeah? I mean, even as you zoom in, it looks really, really smooth, except, I mean, it's a singular continuous function. So this thing has 0 derivative almost everywhere, right? And it turns out this is strictly increasing. It's kind of a complicated example of a strictly increasing singular continuous function, but it is. All right, and here's the first sort of general result, which I finally got to put a date on it because it was just accepted maybe like a few weeks ago, right? And so this is joint with James Evans was my recent PhD student, and Neil Manibo, of course, I think everyone knows in this crowd now. And what we did is we extended this. So the idea now is you still have any regular sequence F, it's K regular, when you sum it between its powers of K. So think of this as summing over the matrix products were all words of length n plus 1, I guess, right? Yeah, K to the n is length n plus 1. Yeah. This is a linear recurrent sequence. Okay. And this is sort of, if you're kind of bored, try and prove it. It's not too hard to see. Okay. And then what we do is we exactly produce the same sort of thing, right? We looked at the type of integers we can get. So this K minus 1 indicates you can't have a 0. You can't start an integer with a 0. So we put K minus 1 there. Yeah. And we did the same thing, evenly distributed, place the weights in the interval the right way, normalized by the sum, and look at what you get. It turns out that if you have a few little constraints on your matrices, then your life is pretty good, and these things exist. One of them is, so at first, we need sort of the equivalent of a Perron-Frobenius eigenvalue. When you look at the sum matrix, we need that to have a unique dominant eigenvalue. Okay. And we'll make these things be real. We want this to be a Perron-Frobenius eigenvalue, like you would want in a substitution system. Yeah. And for us, one of the nice things is let's assume that the spectral radius of that sum is strictly larger than the joint spectral radius of the finite set you care about. Okay. That actually helps you with some uniqueness results. It helps things converge, essentially, for us. Okay. And essentially then what you get is that you produce the distribution function first, right? If that distribution function, and I shouldn't call it a distribution function yet, but you produce this curve that will be the distribution function, as long as that is bounded variation, you can sort of define this Riemann-Stieltjes measure off of it, and that is what we call the ghost measure. This is this measure associated with the regular sequence. Okay? And it turns out as long as this condition holds, the spectral radius is bigger than the joint spectral radius, it's a continuous measure. Okay, so that was nice, but this is just kind of classifies all continuous ones. Should be all right here. So a little bit about the proof, and I mean very, very little. Okay? It turns out that this proof is related to dilation equations. Yeah, so 2-scale dilation equations. So what you do is you look at sort of if you have a k-regular sequence, you look at these sort of, well, this difference equation. So this difference equation, these arise in the study of wavelets, several different things. And if you want to know a lot about dilation equations, you should read Jeff Lagaris's 2 papers in the 90s with Ingrid Dobeschies, which I'm now forgetting what they're called, but they're all about dilation equations. So why this is interesting is we produce one by taking our finite set of matrices, these BAs. Yeah, so we place them in our dilation equation. This rho is the Perron-Frobenius eigenvalue of the sum. Yeah. And it turns out these things, the solution exists and is unique, provided that rho is bigger than rho star. This is why we assume that rho is bigger than rho star, because we wanted to use this theory, and we wanted a nice, unique solution. Okay. And so what happens is you can actually just write down the distribution function of this measure you produce based on the solution of the dilation equation. Okay. Now, if you've read through some of the solutions, some of these dilation equation papers, you realize these are related. They're very geometric. They sort of produce solutions to iterated function systems. Yeah. And Jeff and Ingrid in their paper have sort of nice drawings sort of indicating this. Yeah. Okay. The next part. Zaremba, Salem, and the fractal nature of ghost distributions. Okay. So these were the pictures that we had before. Yeah, and I said there must be something geometric going on. And we've already now established that these things are connected to dilation equations. Yeah, so maybe now there really is something geometric going on. Yeah. So let's produce this, what do you call it? The distribution function for the Zaremba sequence, this 2 Zaremba sequence. Okay. Now, what I'm doing, so this is sort of the second step here. Yeah, so this is my 2. Yeah, and I'm just going to look at the sequence of pictures here for k going up. So what I'm doing is looking at the distribution function of the limiting points. Yeah, except I should have, I cheated because I don't know how to draw lines in Maple. So when I have a point, it should have a line to the other point, right? To be a real distribution function on the interval. But let's wave our hands at that. Okay, and just assume I have sort of straight lines, step functions, yeah, and see what happens. So I'm just going to go increase the power of 2. It's my equivalent of a movie. And once you get to 11, it's filled in and you can't really see much else, right, in this picture. Now what this is, if you think about it here, what I've done is I've looked at the partial sums of the sequence now, and instead of dividing it by this, say, power of k, I should say, right? So remember, if I summed up to x, I divided it by x squared, right? And as x grew, that was a function that was different, yeah? But here in the interval, I'm dividing it by one number, yeah? And so because I have a non-negative sequence, this is going to be sort of growing, yeah? And essentially what one has done is one's taken that picture of the Dolomites and stretched it out, fighting this x squared, yeah? Making the contribution of the x squared essentially go away and then normalizing it to the interval. Okay, so all of the sort of the fractal behavior that one has is sort of still in there, connected to the sequence, but it's taken away this x squared. So we looked at this picture and we said, gosh, I've seen that before. Has anyone seen this before? No one's read my paper then, right? That's not, it's embarrassing, no. Well, we did, and actually this is something that my PhD student said, oh, I just read this paper and I've seen this picture. Oh, cool. Well, he just read this old paper from Salem in the 40s, where what Salem was trying to do is do a really easy sort of geometric construction of a strictly increasing singular continuous function. Okay, and this is an example now you can find in Billingsley's probability measure book. It's sort of everywhere, I guess. Yeah. I have to say though, when Salem did it, he said geometric construction, but there were no pictures in his paper. Yeah. So for me, I need pictures with my geometry. And so we produced this picture. And this is this one here on the right. This is sort of this bumpy sequence. And what one does is just starts with the iterated function system here. Yeah. So if you look in Billingsley, you'll see, and in there you'll see the 3/5 and the 2/5. So you'll have sort of 2/5 y for one, and then 3/5 y plus 2/5, and you iterate that. But I want to keep track of the addresses as well. And so this is why I've sort of put this 1/2 up here. Okay. So then I can actually just plot X and Y and get these pictures, right? And so when you apply this just to start with this line that connects 0 to 1, 1, and iterate. So I've drawn in the iterations and just keep going, you sort of get this picture, and then you can put them side by side. So this is my Salem, I would call it the Salem attractor. It's the attractor of the iterated function system. And this is the Zaremba ghost distribution. And I look at those and I go, gosh, they're the same, right? And so I had this undergrad student, Zach Groth, he was the other one on the joint work with. And I said, you should go prove those are equal. And of course, he went out and he tried and he realized a week or so later, well, they're not equal. Yeah, boy, they look equal. And I mean, you print them out, you put them like this, they look equal. So, but he was smart and he asked a computer. And it turns out this is the difference. So this is Salem minus Zaremba. And I realize you guys are far away. If you could see the dash marks, the largest difference is 0.003. That's pretty small. We thought, gosh, maybe that's computer error, right? I mean, maybe I did something dumb, but no, in fact, they really are different. Yeah, and how do we see they're different? Well, this is this connection from dilation equations to iterated function systems. So if you have a dilation equation, yeah, and you want to look at the solution of that, that's part of a solution to an iterated function system. And you can just write down the iterated function system. So if I have these B matrices, just like in the beginning, I had this sort of 2/3 for the Salem one. I had what 2/5 and 3/5. Yeah, 2 and 3 are kind of my matrices there. This 5 was my spectral radius of the sum because the sum is 5 1-by-1 matrices. Yeah, and so this is what you place in sort of your say lower right hand corner. I want to keep track of addresses, so I put my 1/k in there. Yeah, and then you have to be a little bit creative, and you need to work with the boundary conditions of your dilation equation. But all the boundary conditions were related to was the prone-Frobenius eigenvector of the sum. So this is all stuff that you just have right on hand. Yeah, and when I say a section, here's exactly what I mean. So if I take the Zaremba sequence and I look at the iterated function system, here it is. This is the thing that produces the iterated function system. And so on the left, I plotted the solution of this. Well, I lie a little bit because this is a 3-dimensional system, right? And I've just plotted the first 2 coordinates. Yeah, but it turns out the measure is just this second piece here of the iterated function system blown up into the interval 0, 1. And it's just because integers don't start with 0 values, right? There's actually a theory you could do it so that they're kind of equal and produce that theory. But being a number theorist, I don't like my strings to start with 0. And now why they're different, this system here doesn't live in 2 dimensions. So if you looked at it sort of from the side, you'd see that it doesn't live in the plane. It comes out just a little bit. Yeah. And so these things really can't match up, right? If it really was equal to the Salem system, it would live in 2 dimensions. Okay, so I told you about some geometric constructions, the existence of these things. So now we think of them as geometric objects, but we haven't talked about where they fit in this Lebesgue decomposition. Yeah, the decomposition is sort of only useful for us if we can actually put them into some bins. Yeah, and so this is what we've done. It turns out what we wanted to do, this first result that Neil and James and I had essentially assumed continuity. It gave you continuity, right? We assumed that rho was bigger than rho star. Okay, we in fact had a little bit more general result, but that one wasn't sort of geometrical. Yeah, but now what we've done is we said, in fact, you have a regular sequence. You can reduce it to kind of a better representative. Yeah, and the measures are equal. Okay, so you take a regular sequence F. Let's see here, and it turns out there's a reduced sequence G. Now, these are not the same sequence. If you're interested in sequences, these were not the same. Totally different. In fact, horribly different sometimes. But as long as you you will have a joint spectral radius. The spectral radius and things, you keep these properties actually. As long as these B's are sufficiently reasonable. So here I'm not taking it to be positive anymore, just saying non-negative, and you want these B's to fix a cone. It's sort of a cone condition replaces positivity, more or less. Okay? It turns out that the measures exist and they're equal. So the ghost measure of F exists and it's equal to the ghost measure of G. G is reduced, so you can actually do something with it. Okay, and what do we mean by reduced? Well, one of the problems you get, this is kind of a big slide, but I'll tell you what can happen. You can have this regular, first of all, the normalization you do could be a very strange linear recurrent sequence, right? You could not just have a power of some number. Yeah, linear recurrent sequences can be sort of strange. I mean, I guess they're sort of exponential polynomials, but it's odd to just divide by that and try and do anything arithmetic. Yeah. So in the reduction, you really do get something that's just a product, right? Something to a power. And that's based on that Perron-Frobenius eigenvalue. So you can reduce to the nice situation. Yeah. Also, what a problem could happen is that you may have this eigenvalue. You can have especially if you're not positive now, you can have geometric multiplicity and algebraic multiplicity that are different. And this is an issue. So our proofs really work when you have a one-dimensional eigenspace. Okay, so we want to kind of have things be nice enough. And so the reduction goes into that form. Okay, that's enough about the reduction. The point is, here's my Lebesgue decomposition, is once you do this reduction, yeah, what you get is you get that these things are spectrally pure. So I don't get mixed versions of these measures. Yeah, assuming you have a reduced representation with a Perron-Frobenius eigenvalue that fits a cone. Okay, so there are some assumptions here. Yeah. And so this is really nice. And this follows sort of I guess the standard way is you show some sort of ergodicity result, and ergodicity gives you purity. Yeah. Here, you don't get ergodic in the general sense, you get what's called de-ergodic. Yeah. So there's sort of this special underlying subgroup where these things are working, right? The support of these. And so this is this sort of group of, you take polynomials in 1 over k, and then you want your k minus 1 for this coefficient. And so this is this dense subgroup that you prove ergodicity over. Okay, so now I know I can put them into the bins. How do I do it? Yeah, well, hopefully you just look at these matrices, right? So there's a fundamental inequality here, I say. You take a finite set of matrices, yeah? And so rho star is the joint spectral radius of the matrices. Rho is the spectral radius of the sum, yeah? And you get this nice inequality sort of for free, right? Certainly the maximal value of a sequence, which corresponds to these rho stars, is less than or equal to the sum of a sequence. These are non-negative sequences, yeah? And then this rho over k, this is the average value of a sequence, of the sequence. And so the average value has to be less than or equal to the maximal value. This is sort of how to get this inequality. And you go, well, okay, now I've got some options, yeah? So this right one could be, well, it can be equal or strict. And the left one can be equal or strict. And this is how you place them in these bins. Okay. So for what we saw in the first theorem that I showed you with James and Neil, is that if rho star is less than rho, you get continuity. It turns out this is an if and only if statement, right? So the only way to get a pure point measure out of these things is if rho star is equal to rho. Cool. All right, well, it turns out if this left-hand inequality is strict, so now you assume this one is strict because I want to characterize the continuous ones, yeah? If this left-hand one is strict, then you get singular continuity. Okay, well, and now that one might not be strict. And then you kind of almost get absolute continuity, but you need a little extra condition. This looks like a funny matrix identity. What this means is that your set of matrices doesn't contain a non-trivial subspace. Okay, and then maybe there's instances where we can kind of remove that condition, right? So morally, something we say in Canada and the US, I guess, morally, the reduced system shouldn't have a shared non-trivial subspace, yeah, unless it's one-dimensional. Okay, in which case the rho star equals rho over k is sort of trivial. Yeah. Cool. All right, I'm doing well. One benefit of these, I should say, kind of before going to the questions, is in my head, I look at these as an analog to patch frequency measures. This is not the case, I think, but it's something that I'm trying to convince myself that's worth looking further into. And the reason is that once you have a continuous measure, you actually have a level set construction of these. Yeah, so you know the standard way to make the Cantor set, right? You take it with the interval and you map it to the thirds and you keep going, right? So here you have a level set, and what you do is on these level sets, it turns out that you look at your, I can just do this. You have your new sequence. This is your reduced sequence from F, yeah? And the values of that are sort of the weights that you spread along at the Lth level, yeah? So for me at the Lth level, I have K to the L, K minus 1 times K to the L positions, and I look at the integers that have words of that length, and as I go up, I just place the values of my sequence with those weights, kind of keep dividing by rho as I go down. Rho is that joint spectral radius, or the spectral radius, sorry, yeah? And so this really, but this is done in a very affine way and not in a very self-similar way. These measurements in general aren't self-similar, okay? They're self-affine, but not self-similar. So here's a couple examples just sort of to remind you of some of these things and how to use this fundamental class. So this is the Stern example. This was my periodic piece. This was the picture Uwe made for us. These are the matrices. Now, if I sum these matrices, they have a spectral that has a spectral radius of 3. The joint spectral radius here is the golden ratio, and that 3/2 is a half, right? And so these are all strict inequalities. This thing is singular continuous, but it turns out, I mean, if you look, this is a half. What was that? The golden mean is like 1.6 something. Is that right? So those are kind of close, yeah. And probably that's why it looks so smooth. Sort of the closer you get, the smoother it looks. Because if you think of this thing sort of going toward that, when they're equal, this is absolutely continuous. Yeah. So for the Zaremba sequence, these were my matrices, yeah. And now I've got 4 as my the spectral radius of the sum. Again, they're all strict, yeah. So is this the silver mean? Is that what that's called? I think so. I get nods, good. And then I have 2 over here because 4 divided by 2 is 2. Probably should have just kept it as 4/2, but, and let's see, so this is 2 and that's 2.4 something. That's a little farther away than 1.5 and 1.6, right? So you've got some really jagged looking things going on. Okay, so what do I do with this? Well, this is the question. I now have built these geometric objects. You can classify them. It's sort of a clean little theory, but you need a really punchy result now, right? This is my hope. I like to think this is punchy too, but I want a punchier one. And so I told you these just for real matrices, but as a number theorist, I really want to just look at integer matrices. And that's why all my examples were integer matrices as well, right? Because I'm really interested in this sort of finiteness conjecture for integer matrices. And one of the questions is, when I specialize to integer matrices, what changes? Maybe some things get better. I should sort of have gap results. You could do things with Diophantine sort of stuff. I don't know. That's sort of the next step. Okay. Another next step is you can actually look at I have these measures, take the singular continuous ones, which are the only ones that are interesting for the finiteness conjecture. The other ones I can prove it for, yeah. And say, well, you can develop a multifactorial spectrum for them and try and understand that, yeah. And what you really want for the finiteness conjecture is actually to understand sort of effective versions of these level sets. Essentially, the level set that corresponds to the joint spectral radius, what you want to know is there a rational number in it? That's equivalent to the finiteness property. Okay? Like that 1/3, how I reached a high point in the Stern sequence at a third. Yeah, so that tells me the finiteness conjecture holds for the matrices associated with the Stern sequence. Yeah, and this is can these things be combined with number theoretic methods? My hope would be that one could sort of take this now and understand using, say, something like you have sort of the harmonic analysis of measures here, right? It would seem natural to combine that with something like the circle method, yeah? And say, I do a circle method around something and see, do I get big peaks somewhere? Hopefully those big peaks are around rationals. If that was true, you might be able to show that rational numbers occur in some of these sets. Yeah, but I mean, it's a wonderful dream and gives me a lot to work on in the future. So thank you for your time.